So we want to talk a little bit about how the notion of linearization and differentials can be applied to error in measurement. Essentially, what it is that when we talk about a scientific measurement, we're assuming there's a certain amount of inaccuracy in it. I've built a lot of inaccuracy into this problem, even though I'm sure we could measure the radius of a sphere more accurately than this. But the point is that we can view the error in measurement as like kind of a differential, and we can actually treat it that way mathematically. So let's suppose that I measure the radius of a sphere to be 10 inches plus or minus zero point 0.2 inches. So I'm allowing for the possibility that I'm off by zero point 0.2 inches in the measurement. So what is the question is, if this is how much I measure, how much error I allow in the measurement of the radius, how much error in the measurement of the volume does this translate to? The way you'd approach this is you want to write the volume in terms of the radius. Now we know this from earlier problems, as well as from earlier courses, that volume is equal to 4/3 pi r cubed. That's the formula for the volume of a sphere. So if that's the case, we can write that dv over dr is equal to 4 pi r squared. By the way, don't confuse this with a related rates problem. I know that when you were doing related rates, we did exactly this part of the calculation, and many people assume that therefore anytime they see volume and the derivative of volume, we're talking about related rates, but we're really not. So the derivative of volume with respect to radius, dv over dr, is 4 pi r squared. That means that dv is equal to 4 pi r squared dr. What is that telling us? It's telling us that if I increase the radius of a sphere, or possibly make a measurement error in the radius of the sphere by the amount dr, then dv is the amount that I will increase the volume of the sphere by, or possibly possibly have to account for that much measurement area in the volume. Or more to the point, although this is an exact statement that dv is exactly equal to 4 pi r squared dr, we're going to say that the error in the volume measurement is approximately equal to dv. So here's how we would set that up. What we would say is that dv is equal to 4 pi times the radius, the given radius, which is 10. We square that. And then we're going to treat this as dr. So that's 0.2. So this comes out to 4 pi times 100 is 400 pi times 0.2, which is 80 pi. So what that means is that we can say that the error in volume measurement, given this information, given that we had measured the radius to be 10 inches, with possible error of 2 inches, of 0.2 inches, the error in the volume measurement is potentially 80 pi square inches, 80 pi cubic inches, which is, by the way, it's approximately equal to 251.2 cubic inches. So that's, since we didn't specify decimal approximation or exact value, either of those would be accepted. Of course, on a test, you would certainly want to give the exact value unless the problem specifies otherwise. So all right, so that's the error in the volume measurement. What that means is that if I'm off by 0.2 inches, then my measurement of the volume might be off by 251.2 cubic inches. So the next part of the question is to express that as a percentage of the volume of the sphere. The volume of the sphere, if it's really 10 inches in radius, is going to be 4/3 pi times 10 cubed. So that's going to be 4,000 pi over 3, which is 4186.67. So that's a 10-inch radius sphere has a volume of about 4186.67. So all we would do is we would divide the error in measurement, because we're being asked to express the error as a percentage of the volume of the sphere. So we'd take 251.2 over 4186.67, and that is approximately equal to 0.06, which is 6%. There we go. So that's so what we're saying is that if we're off by 0.2 inches, then in our radius measurement, then our volume measurement is off by 251.2 cubic inches, or approximately 6%. Now I should point out that what we've measured is not the exact. We haven't measured the exact error in the volume of the sphere. We've measured the approximate error because what was going on here was we defined volume as a function of radius. This is v equals 4/3 pi r cubed. I picked a value here, like 10, a radius of 10, and instead of following the actual volume function, instead I followed the tangent line and went right here. So when I went up to 10.2, I found this red dot instead of this purple one. So I didn't find the exact amount of error, but I did find an approximation of the error. That's what was going on graphically.